All right, let's talk about something that's literally everywhere. From the weather forecast you check in the morning to the stock market, we're talking about probability. Now, I know it sounds like some heavy duty math, but really it's just the science of uncertainty. So let's jump right in and try to make sense of it all.
You ask this all the time, right? Maybe without even thinking about it. What are the odds I'll hit snooze one more time and still make it to work? What are the odds my favorite team will actually win this year? It's just a fundamental part of how we think and make decisions. Today, we're going to get you the tools to start answering that question with a little more confidence.
Let's start with a super simple one, a classic. In cricket, the coin toss at the beginning of the match. Well, that's probability in its purest form. You've got two teams, two possible outcomes, heads or tails, and each team has an exactly equal shot. It's a clean, perfect 50-50 chance.
But let's be real. Life is rarely a simple coin toss, is it? Think about a weather report that says there's a 40% chance of rain. That's a whole different ballgame. It doesn't mean it's definitely going to rain, and it doesn't mean it won't. It's a measure of how likely it is, and that number directly affects your plans. Do you bring the umbrella or risk it?
And then you've got the other extreme, the lottery. The chances of winning are, well, almost zero. Understanding these teeny tiny probabilities is just as important as the 50-50 ones. So how do we actually figure all these numbers out? Well, believe it or not, it all starts with something really simple, counting. That's right. Before you can figure out the odds of something happening, you first have to know how many things could possibly happen in the first place. And to do that, you have to answer one critical question. Does the order of things matter?
And this right here breaks down that huge idea perfectly. On one side, you have permutations, where the order is absolutely everything. Think about your phone passcode. 1234 is not the same as 4321. One works, the other doesn't. But on the other side, you have combinations, where order is totally irrelevant. If you order a pizza with mushrooms and onions, you don't care if they put the mushrooms on first or the onions. You just get both.
So let's dig into permutations a bit more. Imagine 10 people walking into a movie theater with a row of 10 empty seats. The first seat can be taken by any of the 10 people. The second seat? Well, now there are only 9 people left, and so on. That's a permutation because every single different seating arrangement is a unique outcome. And get this, by the time you do the math, there are over 3.6 million different ways for just 10 people to sit down.
Now, let's flip that idea on its head with a combination. Let's say you're playing cards and you get dealt a 13-card hand. Do you care what order those cards came to you in? Of course not. An ace of spades is an ace of spades, whether it was the first card you got or the last. The only thing that matters is the final group of cards you're holding. That's the difference, right there.
Okay, so now that we have our tools for counting, permutations and combinations, we can finally build the formula for probability itself. This is the heart of it all.
And here it is, the core idea. And it's actually just a simple fraction. The number on top is what you want to happen. Let's say rolling a 6 on a single die. There's only one way for that to happen. The number on the bottom is the total number of things that could happen. In this case, 6 different faces on the die. So the probability of rolling a 6 is just 1 out of 6. Simple as that. And here's a crucial point. Probability always lives on a scale from 0 to 1. 0 means it's totally impossible, like, being in 2 places at the same time. 1 means it's an absolute certainty, like the sun rising tomorrow. And if you take every single possible outcome and add up their probabilities, they will always, every single time, add up to exactly 1.
All right, enough theory. Let's see how this actually works in the real world. We're going to analyze a really simple casino game to see if it's a good bet or a sucker's bet.
Okay, so here are the rules. We've got a bag with 1 red ball and 1 blue ball. We're going to draw a ball, check the color, and then, this is important, put it back in the bag. We do this 4 times. If we manage to pull out 4 red balls in a row, we win 200 rupees. Any other result, and we lose 10 rupees. So the big question is, should you play this game?
So using what we've learned, we can map out the odds. And what we find is pretty interesting. The chance of getting all 4 red balls, the only way to win, is just 1 in 16. That's it. Meanwhile, the most likely thing to happen is getting 2 reds and 2 blues. This chart makes it really clear. The winning outcome is actually the least likely thing to happen.
So how do we actually decide if that one winning chance is worth the risk of all those losses? Well, for that, we use a super powerful tool called expected value. It's a way of calculating the average result of a bet if you could play it over and over and over again, like an infinite number of times. It basically tells you if a bet is smart in the long run.
So we run the numbers. We take that big prize, the 200 rupees, and we weigh it by its tiny 1 in 16 chance of happening. Then we take the small loss, 10 rupees, and we weigh that by its much, much bigger 15 in 16 chance. We put it all together, and we are left with this number, a positive 3.125.
So what on earth does that mean? It means that, on average, every single time you play this game, you can expect to win about 3 rupees. So if you sat there and played 1,000 times, you'd walk away with over 3,000 rupees. For you, the player, this is an amazing game. For the casino, it's an absolute financial train wreck. Now, that game was an example of what we call discrete probability. We had a limited number of outcomes. But what about things that can take on any value, like a person's height or weight? For that, we need to look at a very, very famous pattern in nature. First, a quick but important difference. The number of red balls we could get in our game was discrete. It could be 0 or 1 or 2, 3 or 4, but it could never be 2.5. In contrast, something like weight is continuous. You can weigh 60 kilograms or 60.1 or 60.11, and on with infinite possibilities in between. And when you plot tons of continuous data from the real world, like heights or test scores or manufacturing errors, you almost always see this shape emerge. The normal distribution. But you probably know it as the bell curve. It's this perfect symmetrical curve where most of the results are clumped right there in the middle, around the average. And the best part about the bell curve is it comes with this amazing shortcut, like a cheat code for statistics. It's called the 68, 95, 99.7 rule. All it says is that for any data that follows a bell curve, about 68% of it will be within 1 standard step of the average. About 95% will be within 2 steps, and pretty much everything, 99.7%, will fall within 3 steps of the average. It's an incredibly powerful way to make predictions. And you might be thinking, okay, that's a neat theory, but check this out. This is real data from the source material showing the heights of 50 actual employees. And look at that. It forms an almost perfect bell curve. Most guys are around the average height, and you have very few who are extremely tall or extremely short. This pattern isn't just in textbooks, it is really, truly everywhere. So, from a simple coin toss to the fundamental shapes that govern our world, probability gives us a language to talk about uncertainty. We've seen how to count all the possibilities and how to calculate the odds to find out if a bet is truly worth it. So the last question is for you. Now that you know the rules of the game, what uncertain decision, what forecast, what gamble in your own life will you look at in a completely new way? Thanks for tuning in.